Okay, then welcome again for this presentation. This is about statistics we have on COVID-19 and especially statistics we have on infections with coronavirus 2. There is a bias in the statistics, and the question is how can we remove the bias that is caused by testing in CoV-2 statistics. Statistics gained a lot of reputation during the current COVID-19 pandemic. Why do I say this? Well, we all study the curve. Everybody studies the curve. So what is the curve? Well, it's a curve that shows the number of infections per day or during the last 7 days or whatever type of curve we look at. And one of the standard questions is the curve becoming flatter? Or what are the infections per 100,000 inhabitants over the last 7 days? And should we react to this? Should public health authorities react to this? Should we react as of 35 or 50 infections per 100,000 inhabitants over the last 7 days? So everybody studies this curve. Here's a standard example. When you look at this from RKI, then, well, we would like to understand what this curve tells us. So what are the questions of this presentation? As I just said, what do these numbers actually mean? What does it mean when we talk about a second wave? What is the intuitive interpretation of the curve? The intuitive interpretation goes, the higher the number of new infections, the more severe the epidemic. So when infections go up, we are all worried, and discussions on public health measures start. What is the argument of this presentation, of the underlying paper? There's a paper belonging to this presentation. The reported numbers of CoV-2 infections, so we need to be precise here, infections with the coronavirus 2, and distinguish this from COVID-19 cases, so really a disease. The argument of this paper is that the reported numbers of CoV-2 infections are not comparable over time. So when we report, let's say today we have around 2,500 new cases in Germany. These 2,500 new cases in Germany today do not have the same meaning as they had 3 months ago, say in April or in May. What do they then mean? Well, if we want to understand what these numbers mean, we need an enlarged SIR model. The CR models are the standard models in epidemiology. We need to enlarge them to understand which data we actually need to have a measure of the pandemic that is comparable over time. And with this new measure and with the data that we need to compute this measure, and the data is very simple, but it's not public, with this data, we can then construct an intertemporally consistent severity index of an epidemic. Why is it that official numbers have problems? Before I go into the main part of the talk, let me give you the answer intuitively. Official numbers have problems because of the types of testing. What do I mean? Well, it's not simply one type of test we undertake. We undertake tests for several reasons. If we had only one reason for which a test is undertaken, then everything would be fine. Then we would have a measure that is comparable over time. So let's imagine we test for SARS-CoV-2 only in the presence of certain set of symptoms. So fever, a headache, and so on, coughing, of course. If we test only according to one rule, then everything would be fine. But we have different reasons for testing. So one is, of course, test in the presence of symptoms, and I guess this is the most important reason for testing. Then we test travelers without symptoms. Then we undertake representative testing, and we think about testing people that go and visit their relatives in elderly homes, or there are many reasons. We test people in hotspots, and so on and so on. As we have a relative shift in these various reasons why tests are being undertaken, a comparison of the daily reported numbers of new CoV-2 infections does not bear any meaning. We cannot compare this over time. When we understand this bias, we also get an answer to one of the most frequently asked questions in the context of CoV-2 statistics. What is the role of testing? Do we observe a lot of reported infections only because we test a lot? I mean, this is what many people argue. Is it true that if we test half as much, we have half as many cases? Or more to the point, in some statistical, more scientific sense maybe, is the number of infections that we report that are confirmed causally determined by the number of tests? So here's the question again. Is the number of infections causally determined by the number of tests? When I give the answer in a nutshell before going through the details, no. The number of infections is not causally determined by the number of tests when we test by symptoms. And the answer is yes, when we test for other reasons. So when we test travelers, when we do representative testing or other. So after all of these negative news, we cannot trust too much the official numbers. I mean, the counting is correct. It's not that I doubt the counting, but the interpretation is very difficult. After these negative messages, what is a positive one? How do we get an unbiased measure of epidemic dynamics? Well, unbiased severity index can easily be constructed. When we follow the logic of the SEER models, we should count only infections with symptoms. Right now, we count all infections. We take everything together. But this creates an intertemporal bias. So we should count only the infections with symptoms. So the message is simply test for CoV-2. I mean, testing is extremely important. No, we want to identify people who are infectious to others, who can infect other people. So test for CoV-2, but count COVID-19 cases. But we will come to this. So what is the structure of the talk? First, we extend the classic SEER model. Why do we do this? Well, we need asymptomatic cases. So those who are infected, but they don't have any symptoms. And we need to take testing into account. What are the results? Well, we will understand the reasons for the intertemporal bias. We will understand when reported infections rise due to tests and when they do not. So this causality issue. And we will also understand what the positive rate tells us. So the share of positive CoV-2 tests to total number of tests, unfortunately, it doesn't tell us anything. So what is the conclusion then? We present a severity index for an epidemic that corrects for the bias. We describe the type of data, which is extremely simple conceptually and also in terms of collection that is needed for the index. And we stress a lot that the index should be used when we think about public health measures. We shouldn't think about public health measures when we focus on new reported infections. Okay, so let me go through them all. First, what is the starting point? Well, we take this standard SEER model, susceptible, infectious, removed. This is what is behind this. It's a very old model. There are certain summaries and surveys. That's a nice paper here. And we introduce some extensions, and the main ones are first, the belief that true infection dynamics are not observable. So in all of the SEER models I know, in all of the applications currently to Germany, the Ferguson study to the UK, and so on, we all behave, I mean, we did projections as well for Germany, we all take the model as if we could observe the number of infected and infectious individuals. But I think this is wrong. We should start from the assumption that infection dynamics are not observed. And then it's the question, statistically speaking, what is a good measure, a good estimator to get information about these unknown quantities. The second extension we do is we test and we introduce tests into the SEER framework. Okay, so let's start with the classic SEER model, but from the very beginning with this idea that there is a true infection dynamics, but that it's unobserved. No scientist, no politician, no whoever knows what the real epidemic dynamics are in a country or on the world. So this is the SEER model as you would see it in any textbooks on epidemiology. There's the number of susceptible individuals, those who can get infected, everybody on this planet at the beginning of the pandemic. Then there's the number of individuals who are infected and can infect others. So this is why they are called infectious. And then there's the number of individuals that are removed. So you can be removed for two reasons, either you recover or you die. So this is all summarized in this parameter rho C. And this is the parameter with which an individual gets infected. If you want to have an idea from an economic background, this is like a search and matching model on labor market theory. So this is exactly the same background from mathematics, continuous time Markov chains that is used there. So how do we describe this? Well, we have a differential equation that describes how the number of susceptible falls depending on the individual infection rate, depending on the number of susceptible individuals, the number just falls. The more interesting equation is the equation for the number of infectious individuals. When you have a large inflow, because there are a lot of new infections, then the number of infectious individuals rises. When individuals recover very quickly, then the number of infectious individuals, of course, goes down. So there's an inflow, there's an outflow, depending on what is faster, the number of infectious individuals goes up or down. Then we have a residual on the removed individuals. So when you recover, then everything is fine. So we have tildes here on these variables because they indicate we don't see this. We cannot observe this. Now we model symptomatic and asymptomatic cases. This is the first extension we introduce here to this model. This was one of the big issues at the beginning of the epidemic when we were still a bit hoping maybe for herd immunity. So at the beginning, a lot of people asked how many asymptomatic cases are there, and if there had been 1,000 times more asymptomatic cases than symptomatic cases, we could have hoped for herd immunity, but we are far away from this, and the ratios are 1 to 3 or 1 to 7 or this order of magnitude. But this was a very big, important question at the beginning, and we need it also for our analysis. So we introduce asymptomatic cases in the SEER model. We split the true number of infectious individuals, which is not observable, into the number of individuals that have symptoms and the number of individuals that are CoV-2 infected but don't display symptoms. And then we have differential equations for the number of symptomatic individuals, for the number of asymptomatic individuals that follow the same logic. There's an inflow with a certain arrival rate, you get infected. There's an inflow into the pool of being infected and having symptoms, then there's a recovery rate, and the same is true for the asymptomatic cases. So this extension is very simple. When you want to have this in mind or get a more intuitive idea, let's look at the following figure. Let's look first only at the lower part. So the lower part is here. The red part, this is the textbook SIR model, susceptible, infectious, and removed. Now we add here with this black circle the asymptomatic cases. Here are the rates with which individuals get infected, and here are the outflows. So individuals recover or some die. So this is the extended SCR model as we have seen it so far. Now we need to model tests for SARS-CoV-2. So how do we do this? Well, we need to take into account what is going on. Various countries have various national testing strategies. What we look at here are 3 reasons for testing. We test because there are symptoms. We test for representative reasons, so scientific studies and other, or we test travelers. And travelers is really just an example of all tests that are being undertaken without symptoms and that are not representative. So let's start. How does testing by symptoms work? Well, when we test by symptoms, and this comes back to the question Ryan just asked, we need to take into account disease dynamics. So individuals can catch many diseases, or let's be more precise, individuals can show up at the GP with a lot of different sets of symptoms. And we could go through this text here, but it's really simpler to return to our figure. So let's look at all the individuals that are here, the susceptible. that can be infected by CoV-2, but you can be infected by many other things. Or you can have a rough throat because you sing too much, because you shout too much, because you drink too much. I mean, there can be many reasons. So people with certain arrival rates, lambda 1, lambda 2, they end up at the doctor with a set of symptoms. One, the flu or a cold, or having respiratory problems for other reasons. And then the doctor decides with a certain probability P1 with symptom set 1, with a certain probability P2 with symptom set 2, or with a certain probability PC when you actually have symptoms that look more like COVID-19. The doctor decides with a certain probability, do we undertake a test or not? And then the test is undertaken, and then actually we observe something for the first time. All of this is not observed, and this is why we have all these dashed lines. In standard data, we don't know how many people have which symptoms, but we do observe, and this is why we have solid lines, we do observe the number of tests, and we of course also observe the population size and so on. Okay, so this is testing by symptoms. Let's continue. Yeah. Okay, so let's return to testing by symptoms. Once we have tested, we now need to know in our model how many tests are there. What is the number of tests and the number of reported infections? So with a probability PI, as we said, a GP performs a test given symptoms I. The probability to get tested with symptomatic SARS-CoV-2 infection is PC. So the number of tests we get is simply the number of tests over all the non-CoV-2 diseases or sets of symptoms, plus the number of tests of actually CoV-2 individuals. And so the number of tests can be replaced by this probability times the number of individuals that have a flu. So if we have a lot of flu and this probability remains constant, then we will have a lot of tests that will all be negative. We assume there are no false positive or false negative tests here in this model. Extension would be simple, but we don't do this. And then the number of tests that actually are related to symptoms and that will show that the individual has CoV-2 infection depends on the number of CoV-2 infected individuals that have symptoms times the probability that a doctor takes a test. So this quantity is not observed, but of course in our model we know what is going on, but in reality this is not observed, but this will be observed. Okay, so as I said before, the number of tests, TD, is really the first variable that is observed. Now we test travelers or we test for scientific reasons. These tests are not related to symptoms. The number of tests is chosen by public authorities, scientists, by available funds for research projects, by capacity considerations, and many other things. So this number is really independent of infection characteristics of the population. And we denote these numbers by TR for representative testings and by TT for testing travelers and all the other tests that are going on. Representative testing is positive with a certain probability PR. This is just a notation, but luckily we know something about this probability. If we truly have a representative sample, then this probability satisfies I tilde divided by P. So what is I tilde again? I tilde is the number of CoV-2 infected individuals at a point in time T. So both with and without symptoms. And we divide this by the population size. So this gives us the probability that a representative test yields a positive outcome. Okay, then we have a certain probability that a test for travelers is positive, and we denote it by PT. So do we know something, about this test, about this probability? No. I mean, it depends a lot on the behavior of the individual. It depends a lot on where the traveler comes from. So this is exogenous to our model. So the total overall number of tests we have in this model is testing because of symptoms. So you test because you want to go to the doctor, then representative testing or testing travelers. Now, let's look at the figure again. We talked about this part already. So there are all these tests that are being undertaken. So these are all ordered by the doctor. Then this is testing of travelers. So you're on some highway and you say, I would like to have a test. I have come from a high risk region, so then you get a test. Or there's some representative testing. Okay, now we need to understand the number of reported infections. The number of reported infections can be split into the reasons for testing. I mean, in our model, this is simple. So the number of reported infections comes from all the sets of symptoms that are actually not CoV-2 related, but there could be a positive, false positive case. We will exclude this in a second. There is the number of reported infections coming from the CoV-2 cases, the number of reported infections from representative testing and from testing travelers. So when we test by symptoms, the probability that a normal test is positive, normal in the sense you're coughing or you have something else, this probability is 0. As I said, we exclude false negative tests here, false positive tests here. So the number of infections reported because we test individuals that have a flu is 0. Now, the probability that a CoV-2 infected individual has a positive test is 1. So we assume the test works perfectly. As I said, we could extend the model. This would be trivial. So for simplicity, we say this is 1. So the number of reported cases of individuals that actually have CoV-2 is given by the number of tests we undertake on individuals that are CoV-2 infected. Then again, this equation which we just saw, because now we test for other reasons. When we undertake representative tests, this yields a positive outcome with the probability PR, the probability we just discussed. It reflects the true number I tilde of infections, symptomatic and asymptomatic. The probability that a test of a traveler is positive is this PT, and we don't know, for the reasons I said earlier and which are now written here, we don't know how large this probability is. It's exogenous to our model. Now, what is the total reported number of infections? Well, we take our equation we saw earlier, we plug in the number of tests for the COVID cases, the number of tests for representative testing times the probability, and the number of tests for travelers times the probability. We can replace this probability by this term we saw earlier. We can replace the number of tests by the probability of the doctor to actually undertake a test of someone that looks like a lot of symptoms that indicate COVID-19 times the number of individuals that are actually symptomatic with CoV-2. And here we cannot do anything with the travelers. We don't know what the probability is, and the number of tests is also sort of exogenous. So this is the equation we get for the number of reported infections in our model. And this is, of course, also something we observe. No, I mean, this is what the media, what public authorities report every day, and what the media repeat every day, if not every hour. Now, let's come to the main question. Are reported confirmed infection numbers biased, or are they unbiased? Well, when we talk about bias, we should be precise. What do we mean by a bias? So let me offer a definition. The numbers of reported infections are intertemporally unbiased if they are proportional to the true but unobserved infection dynamics. So if the numbers we get from health authorities every day are related, are proportional to true infection dynamics, then we would talk about an unbiased measure. Luckily, in our theoretical world, we understand everything, we know everything. In the theoretical world, we observe everything, so we can study and analyze whether a measure is biased or not. So when is reporting unbiased? So there are these good cases. The first good case is when we test by symptoms only. So when we said all the representative testing and all the traveler testing and all the other tests, hotspots, blah, blah, when we all set this equal to 0, then the number of reported infections is given by the number of infections that are identified by doctors that see an individual that has symptoms. So we get this expression that we saw earlier, probability of the doctor to take a test times the number of individuals with CoV-2 infections that have symptoms. So this is a wonderful situation, because then we would know, if this was the only reason for testing, when the number of reported infections goes up, and when we assume that this probability to undertake a test is constant. So capacity considerations shouldn't play a role. That's an important point. That's another reason for bias, but we don't focus on this reason for bias. It's there, yes. So let's assume the probability that a doctor takes a test of an individual that has symptoms is constant. Then if the number of reported infections goes up, we know that the unobserved number of individuals that are symptomatic and infected with CoV-2 also goes up. So we have a good measure, a good estimator, unbiased estimator, maybe even from a statistical perspective. Okay, so what does this also tell us about this issue of causality? So the point down here, the more infections are reported, the more severe the epidemic. So this is a good thing. We have a perfect observation here. And tests here do not have a causal effect on the number of reported infections. So the number of reported infections are not causally influenced by the number of tests. Why not? Well, tests are endogenous. No, I mean, in the theoretical or also in the econometric sense. Tests and infections are driven by some third underlying factor, which is, of course, the true number of infected individuals with symptoms. So both of them are driven by these symptoms in society. So there's, of course, a correlation between the number of infections and the number of tests, but there's no causal relationship. The second way we could get unbiased testing is representative testing. This is pretty obvious. This is why we do representative testing after all. So when we set all the tests due to symptoms and all the tests of travelers equal to 0, then we have number of infections is given by the ratio of infections in society. Now this is with and without symptoms. So this is different to testing by symptoms. So this is I tilde, with and without symptoms, times the number of representative tests we undertake. And of course, when we divide this, we get the so-called positive ratio. We get the number of positive tests divided by the number of tests. And this is a perfect measure of the infection rate in the population. So representative testing provides a measure of overall infections. Now, let's come to the more realistic cases, and this is what is going on in practice in the real world. Let's talk about biased reporting. Let me first illustrate the bias with the example of representative testing, and then I give you a quantitative example, a numerical example with the testing travelers. So why do we have a bias? Because several types of testing are being undertaken simultaneously. So when we first consider symptomatic and representative testing, this is the number of infections that are reported, number of infections coming from symptoms with CoV-2 infection, and representative testing. Now imagine representative testing goes up. So we have more funds and we do more of this. Then the reported cases increase. No, I mean, we are here at a point in time t. So we are on a certain day. And let's imagine we can decide on this day, we can decide today, do we do 10 representative tests or do we do 10,000? Then, of course, on this day, symptomatic cases don't change. No, you're sick in the morning, you don't get sick during the day, you can get sick overnight again, as on a simple illustration. So this is constant. The number of infections, symptomatic and asymptomatic, on this day is constant as well. We vary only this number of tests. So there's no change in the true number of symptomatic cases. There's no change in the true number of symptomatic and asymptomatic cases. Nevertheless, the number of reported infections go up. So they go up simply because we test more. So sorry to say this, but don't build your private plans on confirmed cases of infections, IT. Now let me give you a numerical example of the bias. Now we do simultaneous testing due to symptoms, and we also test travelers. So this is a much more realistic case. Then the reported cases are the number of reported cases because you go to the doctor, you have symptoms, and the doctor finds that you actually have CoV-2 infection. And the number of tests coming from positive tests of travelers. The scenario we're going to study in the next figure is no testing of travelers took place at the beginning of the pandemic. And then at some later point, I mean, this point in time, t equal to 60, I mean, this is just a numerical illustration. I'm not saying this is the real world, it's a numerical illustration. Then as of this point in time, t equal to 60 travelers are being tested. And the number of tests then increase over time, because we have more and more test capacity. Then what is going on? What do we see in this figure? Well, on the horizontal axis, we see time. On the vertical axis, we see the number of infections. And we first start with the true infections with symptoms in our economy, or not economy, in our society. So this is the blue dashed curve. This is what we don't know in reality because we don't observe this, but this is what we know in the model. So this is the true epidemic dynamics. Then when we report only infections that we obtained because we tested by symptoms, so if we reported only this source of tests, then we would get the green curve. And when we have a certain share, let's say 90% is reported or something, because we do have some false negative, then we would get a perfect proportional measure, this green curve, a perfect measure of the unobserved true infections. Okay, now we have the idea that we want to test travelers. And let me stress already at this point, I mean, testing is extremely important. And testing travelers is extremely important because we want to avoid that infected individuals infect others. So it's not that I'm saying testing is not important, but the adding up of different sources of testing, that makes no sense. Because if we add the reported infections, the red ones here, the reported infections from testing travelers, if we add them up with the reported infections that come from testing by symptoms, then what do we see here? Well, the number of reported infections go up. We see a second wave where there is no second wave. I mean, we're in a nice theoretical world. We know there is no second wave. We know the true dynamics, the blue dashed curve. So true infection dynamics, they go down. And reported numbers of infections, they go up. So this is an illustration of the bias which is likely to be there in the data. So let's make two non-applications to Germany because we don't have the correct data at this point and it's not sufficiently detailed. Nevertheless, let's take the number of tests that we get from RKI. Let's take the number of positive SARS-CoV-2 infections. We have here time on the horizontal axis and the number of tests and the number of reported infections. So we observe the number of tests. We observe the number of infections. The question is, can we conclude anything from these two time series about the true epidemic dynamics, about individuals with symptoms and about individual without symptoms, but still being CoV-2 positive? Technically speaking, that's very simple. We have two equations in too many unknowns. And everybody who knows a little bit of maths knows when you have two equations, you can hope to solve for two variables, but you cannot hope to solve for all of these variables which you see on the right-hand side. So true infection dynamics cannot be understood from these two time series. Okay, so we have a problem. We have a problem. Now let's talk about the positive rate. This is a quantity many people use and believe that it's useful. So let's ask, what does this positive rate tell us? Again, what is the positive rate? We talked about it earlier. It's the ratio of confirmed infections. So up here, this is what is reported, to the number of tests. This is the positive rate. It's often discussed in the media. It's discussed also elsewhere in very good, very useful data sets. But the question is, what does the positive rate mean? Again, that's a theoretical question. You can have as many numbers as you want. You always need theory to give an interpretation to numbers. So here's the positive rate in our world, in our theoretical world where we observe everything. What does the positive rate tell us? Okay, let's again be first very positive and optimistic. Generally, what do we want? The question is, does a rising positive rate imply that the epidemic gets worse. So we have more positive cases. Does the epidemic get worse? What does epidemic gets worse mean? Well, we have more CoV-2 infections with symptoms, without symptoms, doesn't matter. I mean, it should be related to the underlying true infection dynamics. When we undertake only representative testing, and this is why it's so useful in this presentation to have representative testing, because it allows to understand when things work, and when you understand when things work, you also understand when things don't work. With representative testing, we know the positive rate is given by the number of infected individuals in society divided by population size P. So with representative testing only, we have a perfect measure, perfect estimator for our true infection dynamics. So when the observed positive rate rises, then we know that the number of unobserved infections is higher. So this is what we would want. Okay, now let's continue. Does this conclusion hold more generally? Let's assume tests are only due to symptoms and traveling, which is quantitatively probably the two most important reasons for testing. So we set representative testing equal to 0. Then the positive rate has the following structure. So this is the number of reported infections. We saw this earlier. Reported infections because people have symptoms, and reported infections because people come back from some other country, some other region, and they undertake a test, and the test is actually positive. And we divide this by the number of tests that are being undertaken. So all the tests because of some symptoms, and the tests because travelers are being tested. And then we ask, when we test more travelers, like in our scenario earlier, when we test more travelers, does the positive rate go up? And the positive rate goes up if this condition here holds. What is this condition? Well, so let's ask, what does this mean? First, technically, when we compute this derivative with respect to dt is in the numerator, it's in the denominator, then we get here a structure which is very familiar from other sources. So it makes sense technically, but technically maybe this is not so important. So let's ask, what does this mean from an epidemiological background with an epidemiological question? It simply means that the positive ratio can rise or fall when we increase the number of tests for travelers. And this positive rate, whether it rises or falls, depends on the number of, I mean, so to say, useless tests. So tests of individuals that have symptoms but are not CoV-2 infected. Of course, the tests are not useless because unless you do the test, you don't know whether an individual is CoV-2 infected. So useless in the sense that you don't find anything. So it depends on this number of tests. It depends on the number of tests related to CoV-2 infections. And it depends on two probabilities. So this condition, when you study it, it's quantitatively absolutely not obvious. So what can we then conclude then from this question? Well, the positive rate, or from this derivative and this condition. Well, the positive rate, it doesn't tell us a lot. It don't mean a thing. So whether the positive rates rises or not, it doesn't give us information about the true epidemic state. So the positive rate is not as, I mean, honestly, believe me, I mean, this is not, I mean, trying to tell some stories, but this is not results I like. No? I mean, but we need to look at what we understand and what numbers we look at and whether they mean anything. So the positive rate, to the best of this analyzing, and there's a paper, everybody can look at the paper, the positive rate is not informative. Okay, now let's become positive at the end of this talk. What is an unbiased severity index? What should we do? Well, the index is extremely simple. The index needed for the severity of an epidemic, which is comparable over time, the index should reflect the number of individuals with symptoms. As simple as that. So the index is simply ID. So the number of infections that are reported because we tested individuals with symptoms. I mean, laboratories tested because doctors said they should be tested. because then we get the number of COVID-19 cases. And this then would be comparable over time. Alternative would, of course, consist in representative testing, but no country can afford to do representative testing every day. So this is a theoretical alternative, but it's not realistic in practice. So what are the data requirements that we need? I mean, they're really small. All we need to do is we need to classify tests by the reasons for testing. So if we have the number of tests reported by public authorities, we need to know why was the test undertaken. Does it come from a highway? Does it come from a scientific experiment? Does it come from a doctor? What we do know, at least for Germany, is where it comes from. Does it come from the doctor? Does it come from the hospital? Or are there other reasons? But we don't have more information. At least the public doesn't have more information. So we would need the reason why the test was undertaken. And well, we don't need a general nationwide agreement to do this. I mean, any region, any Bürgermeister or Landrat, no German language, sorry for this, or any local health authority. Then we would have data on COVID-19 cases, national and regional. And then everything would be fine. Then we would have a intertemporally comparable measure of the epidemic. And then we would be able to say when should public health measures become stronger and when not. Okay, so let me summarize. What was the starting point? The starting point was we don't observe epidemic dynamics, true epidemic dynamics. So this is why we test in the reality, and we need to take the testing into account in our model as well. What are the findings? The changes in the testing, the reasons for testing biases CoV-2 statistics, and this is what we look at every day. They are biased. So reported numbers of CoV-2 cases are not comparable over time. So when in Germany we think about massive Ausweitung von Tests, no, we think about more and more tests being undertaken, then yes, please do this. This is a fantastic thing. No? I mean, because we want to identify people who can infect others, but don't count this. Don't count the number of positive cases coming from one source and another source and add everything together. Sort tests by reasons for tests. So what is the way out? Count the number of CoV-2 cases with symptoms. So in other words, very, very simple, count the number of COVID-19 cases. Do not count the number of CoV-2 infections. Okay, that's all I wanted to say. Thanks a lot for your attention.